All right, science fans, buckle up. We're diving into a world of invisible forces, a world that powers your phone, your computer, and even makes your doorbell ring. I'm talking about magnetism and electricity. For a long time, people thought these two were totally separate. Like, your fridge magnet had nothing to do with the lightning in a storm. They were like two different superheroes, living in different cities, never crossing paths. But then, science happened. Scientists, you see, are super curious people. They love to poke things, prod things, and ask why. And in the early 19th century, some really smart folks started noticing some weird connections. It wasn't a big eureka moment at first. It was more like a series of, that's odd moments. They saw little hints, tiny clues that maybe, just maybe, electricity and magnetism weren't strangers after all. Maybe they were part of the same amazing, fundamental force of nature. Think about it. Two forces, seemingly different but secretly connected. This idea that electricity and magnetism were linked was revolutionary. It was like finding out that peanut butter and jelly were not just good apart, but incredible together. This connection is called electromagnetism. Say it with me, electromagnetism. It's a big word, but it describes an even bigger idea, an idea that changed the world. It paved the way for so many inventions we use every single day, from the giant generators that power our cities to the tiny speakers in your headphones. Get ready, because we're about to explore how these amazing connections were first spotted and how they led to the incredible world of technology we live in today. It's going to be electric and magnetic. Now let's talk about one of those, that's odd moments. It happened in 1820. Our science hero for this part is a Danish physicist named Hans Christian Oersted. Professor Oersted was giving a lecture. He was showing his students how electricity flows through a wire, a current. He had a battery, some wires, the whole setup. Pretty standard stuff for a science demonstration even back then. Nearby on his lecture table there was a compass. Just a regular magnetic compass, the kind that points north. It wasn't even part of the experiment. Or so he thought. But then something amazing happened. Every time he switched on the electric current in the wire, the compass needle twitched. It moved. It danced away from pointing north and tried to line up perpendicular to the wire. Can you believe it? An electric current was affecting a magnet. This was totally unexpected. It was an accident, a beautiful scientific accident. Oersted was probably a bit surprised, maybe even a little confused at first. Wait a second, he might have thought. What's going on here? He turned the current off. The needle went back to pointing north. He turned it on again. The needle danced again. This wasn't a fluke. He repeated it over and over. This simple observation was huge. So, we know that moving electric charges, like the current in Oersted's wire, can create magnetic fields. And we know that magnets can push or pull on other magnets. But what happens if you have a moving electric charge, like a tiny electron, zipping through a magnetic field that's already there? Does it feel a force? You bet it does. And this force has a super cool name. The Lorentz Force. It's named after another brilliant physicist, Hendrik Lorentz. This force is like the traffic cop of the subatomic world, telling charged particles where to go. Now, the Lorentz Force is a bit special. It doesn't just push or pull in a straight line. Oh no, it's way more interesting than that. The direction of the Lorentz Force depends on two things: the direction the charge is moving and the direction of the magnetic field. And here's the really neat part. The force is always perpendicular to both of these. Okay, we've seen that a single charged particle moving in a magnetic field feels the Lorentz force. Now, what happens if you have a whole bunch of charges moving together, like, say, an electric current flowing through a wire? Well, if that wire is sitting in a magnetic field, each one of those moving charges inside the wire feels a tiny Lorentz force. And when you add up all those tiny forces on all those billions and billions of charges, you get a big, noticeable force on the wire itself. This is called the motor effect, and it's seriously cool. Imagine a wire carrying current just chilling out. Then you bring a magnet nearby. Suddenly the wire might jump, or get pushed, or pulled. It's not magic, it's physics. The magnetic field is exerting a force on the current-carrying wire. The direction of this force, just like the Lorentz force on a single charge, depends on the direction of the current and the direction of the magnetic field. We even have a handy way to figure it out, often using another version of the right-hand rule or left-hand rule depending on convention. Section 5. Particle Party, Zooming Charges in Magnetic Mazes. We've talked about the Lorentz force making charged particles turn. Let's zoom in on that a bit more because it's super important and leads to some amazing science and technology. When a charged particle, like an electron or a proton, enters a uniform magnetic field at a right angle to the field lines, something really neat happens. The Lorentz force, always acting perpendicular to the particle's velocity, doesn't change the particle's speed. Instead, it acts like a constant turning force, guiding the particle into a perfect circular path. It's like the particle is on a magnetic merry-go-round. The radius of this circle depends on a few things: the particle's mass, its speed, its charge, and the strength of the magnetic field. Faster particles or more massive particles will make bigger circles. Stronger magnetic fields will make tighter circles. Scientists can use this. By measuring the curve of a particle's path in a known magnetic field, they can figure out things like its momentum or its charge-to-mass ratio. It's like being a detective for subatomic particles, using magnetic fields as your magnifying glass. This is crucial in experiments that discover new particles. Now, where do we see this in action? Particle accelerators. Section 6 Magnetic Field Math. Biot-Savart and Ampere to the rescue. So we know that moving charges and currents create magnetic fields. Oersted showed us that. But scientists are never satisfied with just knowing something happens. They want to know, how strong is that magnetic field? What direction does it point in? To answer these questions, we need some math. Don't worry, it's cool math. Two very important laws help us calculate magnetic fields: the Biot-Savart Law and Ampere's circular law. These are like the secret recipes for figuring out magnetic fields. First up, the Biot-Savart Law, say Biot-Savart. This law is super useful for calculating the magnetic field produced by a small segment of a current-carrying wire. It tells us that the little bit of magnetic field, dB, from a little bit of wire, dl, depends on the current, I, the length of that little bit of wire, and its orientation relative to the point where you're measuring the field. Section 7. Supercoils, solenoids, electromagnets, and lifting heavy stuff. Now that we know how to calculate magnetic fields, let's talk about some really cool applications, especially using Ampere's law. One of the most useful arrangements of wire for creating a strong uniform magnetic field is called a solenoid. Imagine taking a long piece of wire and wrapping it into a tight coil, like a spring or a slinky. That's a solenoid. When you pass an electric current through this coiled wire, something amazing happens. A surprisingly strong and remarkably uniform magnetic field is created inside the coil, running along its axis. It's like creating a magnetic tunnel. The strength of the magnetic field inside a solenoid depends on a couple of things: the amount of current flowing through the wire, and how many turns of wire you have per unit of length. More current? Stronger field. More turns packed closely together? Stronger field. And the cool thing is, the field outside a long solenoid is very weak. So all that magnetic power is concentrated right where you want it, inside the coil. This makes solenoids super useful for all sorts of things, from controlling valves in your washing machine to being key components in medical MRI machines. Section 8. Current attraction, parallel wires, and magnetic twists. We know a current-carrying wire creates a magnetic field around it. And we know that a current-carrying wire placed in an external magnetic field experiences a force, the motor effect. So, what happens if you put two current-carrying wires near each other? Well, the first wire creates a magnetic field. The second wire is sitting in that magnetic field, so it feels a force. And guess what? The second wire also creates its own magnetic field, and the first wire is sitting in field, so feels a force too. It's like they're interacting with each other through their magnetic fields. How cool is that? Now here's the really interesting part. If the currents in the two parallel wires are flowing in the direction, the wires will actually attract each other. They'll pull together. It's like they're buddies, drawn to each other by their shared current flow. But if the currents are flowing in directions, the wires will repel each other. They'll push apart. It's like they suddenly disagree and want some space. This attraction and repulsion between current-carrying wires is a direct consequence of the magnetic forces at play. You can even demonstrate this in a lab with some fairly simple equipment. This force between parallel wires is actually super important. It's so fundamental that it's used to define the ampere, the basic unit of electric current. Section 9. Spinning needles and our electric world. Galvanometers and why magnetism rules. So, we've seen how currents create magnetic fields and how magnetic fields exert forces on currents. How can we use this to measure things? Let's talk about a clever device called a moving coil galvanometer. This instrument is designed to detect and measure small electric currents, and its operation is a beautiful demonstration of the principles we've been discussing. At its heart, a galvanometer has a coil of wire suspended in a magnetic field, usually provided by a permanent magnet. When a current flows through the coil, it becomes an electromagnet and experiences that magnetic torque we just talked about. This torque tries to twist the coil, but the coil is attached to a spring. The more current flows, the stronger the magnetic torque, and the more the coil twists against the spring. Attached to this coil is a needle, or a pointer. As the coil twists, the needle moves across a calibrated scale. So by looking at how far the needle moves, you can tell how much current is flowing.